Hello everyone, Mr. Nawadata here, and I'll be going over intermolecular forces homework today. So, let's get started. For question 1, it asks, what is a dipole moment? Well, a dipole moment is when a molecule has an uneven distribution of charges. Think back of how atoms share electrons. It's not always even. Some hold the electrons closer to each other, and that's what causes the dipole moment. Well, what happens to the forces between the two charges as the distance between them increases? Well, this is a callback to our good friend Coulomb and Coulomb's law. And his law states that as our distance between our charges increases, the force between them decreases. Now, what's the difference between intermolecular forces and intramolecular forces? Well, the difference is in the root of each word. Intramolecular forces are the forces within a molecule, so the bonds that hold these two atoms together. Intermolecular forces are the forces between two molecules, and those are holding the molecules together. For question 4, it asks, what are 3 intermolecular forces? And that's easy. 1 is the London dispersion forces. 2, dipole-dipole. And 3, hydrogen bonding. And we're going to talk about each of these a little bit more in depth in the following questions. So what causes London dispersion forces? Simply put, London dispersion forces are temporarily induced dipoles, and this is due to nearby charges. The key word is temporary. Just like when you rub a balloon against your hair, some of your hair sticks to the balloon, but it's not permanent. When molecules come close to each other, they will create these temporary dipoles, but once the molecule passes, it'll go back to normal. What about dipole-dipole forces? Well, these are permanent dipoles that are due to the uneven sharing of electrons. Atoms with larger electronegativities will tend to hold electrons closer to them, causing this uneven distribution. This is not temporary, as the dipole will stay until the molecule is broken. Now, let's talk about hydrogen bonding. What elements can cause hydrogen bonding? It's a long list of elements, so here we go. The elements that can give a rise to hydrogen bonding are nitrogen, oxygen, and fluorine. Which one needs to be present every time? Well, hydrogen. It wouldn't be called hydrogen bonding if it didn't need hydrogen present. For question 8, we have to draw a water molecule and show why it has a dipole moment. Now, if we draw the dot structure, it's not going to be much help. We have to look at the molecule in 3D. When we look at how the electrons are being shared, these are going to be pulled from the oxygen with the same force in the same direction. So they're going to cancel each other out. Let's focus on the lone pairs. So if we rotate our water molecule, with this being the front side, it's not perfect, but this is just to show you how the lone pairs are actually separated from each other. The lone pairs are going to be pulling with the same force. This one is going to be up and right. This one is up and left. The left and right portions are going to cancel, and the only thing that is going to be left is this up direction. So our dipole would be in the up direction. For number 9, we have to tackle the question of, well, why is water a liquid at room temperature? Simply put, this is due to hydrogen bonding. Hydrogen bonding is not the strongest, and because these molecules are always moving, that energy is enough to break those hydrogen bonds, causing it to be liquid at room temperature. For 10, it asks, draw the structural formula for CH4, methane. Are the bonds polar covalent? And does the molecule have a dipole moment? So if we draw the dot structure, it's not going to be much help. So if we try to draw its molecular shape, here we can see how the hydrogens are interacting with the carbon. Each of the hydrogens are pulling, and there's also this one on top. Because it's a tetrahedral, and all of our atoms that are attached to it are the same molecule, all of these forces from the hydrogen are going to cancel each other out. So is our molecule polar? No, it's not polar. And because of that, it is not going to have a dipole moment. For 11, we have to do similar steps, but now with sulfur hexafluoride. So let's draw our dot structure. So it should look something like this. And again, dot structures aren't going to be that much helpful. So we have to draw it in its 3D form. Looking at our molecule, our fluorines across from each other are going to cancel out. And the only one that's going to be left remaining is going to be our lone pair. So in this case, we end up with a polar covalent molecule. And because of that, we are going to have a dipole moment. And our dipole moment would look something like that. Next, same thing, but now with ammonia. So drawing our dot structure looks something like this. And again, our dot structures might not be that helpful. So we have to draw it kind of in 3D. Doing our best to draw it in 3D. Here we see these hydrogens are all going to be pulling. And in their own direction, that direction would cancel out. However, this lone pair is going to be stronger than the remaining force that's up from the hydrogen pulling down. So in this case, we are going to have a polar molecule. And because of that, we're going to have a dipole moment. And it's going to be pointing towards our lone pair. Next, we have our hydrogen molecule. So when we draw our dot structure, it looks something like this. Here, both of these hydrogens are going to be pulling with the same amount of force. So we're going to end up with a non-polar molecule. And because it is not polar, we are not going to have a dipole moment. For our last one of this section, we're going to be working with carbon dioxide. So when we draw our dot structure, it should look something like this. Remember, our carbon is going to be double bonded to each oxygen. And because of that, we're going to end up with a linear molecule. And just like our hydrogen example, because it is linear, we're going to end up with a non-polar molecule. Each of the oxygens are going to be pulling with an equal amount of force. And because of that, we are not going to have a dipole moment. For our next section, we have to identify the molecular forces that would be present in each of the following species. So here we're going to be working with a hydrogen molecule. So just going down the list, London forces. So will it be able to have a temporary dipole? Yes. For dipole, for me, I'm just going to think about it, is it going to be polar? And looking at my hydrogen molecule, it's going to be a linear diatomic. So it is not going to be polar. So it won't have a dipole. And lastly, for hydrogen bonding, is my hydrogen going to be bonded to nitrogen, oxygen, or fluorine? Since it's a diatomic, it's not going to be bonded to any of those. So it's not going to have hydrogen bonding. Next up, we have hydrochloric acid. Can we induce a dipole on hydrochloric acid? Yes. Is hydrochloric acid polar? Yes. The chlorine has a higher electronegativity. And is there a bond present between nitrogen, oxygen, and fluorine? No. So no hydrogen bonding. Next up, we have our water molecule. Can we induce a dipole? Yes. So yes for London. Is it polar? Yes. And is a hydrogen bonded to a nitrogen, oxygen, or fluorine? Yes. Next up, we have ammonia. Can we induce a dipole? Yes. Is it going to be polar? Yes. And you can go back to the previous questions to check our dipole. And is hydrogen bonded to nitrogen, oxygen, or fluorine? Yes. So all three forces are going to be present. Next up, hydrofluoric acid. Can we induce a dipole? Yes. Is it polar? Fluorine has a higher electronegativity, so yes. And is there a hydrogen bonded to nitrogen, oxygen, or fluorine? Yes. So all three forces. For our last one, we have sodium fluoride. Can we induce a dipole? Yes. Is it going to be polar? Well, fluorine has a higher electronegativity, so it is going to be polar. And lastly, do we have a hydrogen bonded to a nitrogen, oxygen, or fluorine? We do not. And that's going to be it. If you have any questions, don't forget to send myself or Mr. Morgan a message on Schoology. Other than that, stay safe, and I'll see y'all next time.